So building the model, let's build the model, and we will build DeepONet model. So we will call it DeepONet. So here we will just give some space, and we will start by saying here class DeepONet net, and it will be neural network module, same as building any like neural network using PyTorch. Def initialization of the whole thing, we self and neurons equals 40, and int in1 will be, well, just initialization to in1 equal 1, in2 will equal to 1, and I will explain, just output neurons equals 20. So what does it mean? So what means is we will take the whole lines and we will turn them, or we will take the whole data, the whole line, the 100 points, and we will turn them into 40 lines. This is so we will compress them a little bit. And for the first value, we will take one value and we will expand this value into 40 neural network, neural points. This is why we will use it. But again, you can just build it different ways. So in1 is going to be our input, the first input, and this is going to be the second input. It's important because this time we are building a branch and trunk. So we will have the first input will be the whole values of the sequence, and input 2 is going to be the location which we are calculating these values. So here input 1 and input 2, and output neurons going to be 20, and 20 is just also another number. These going to be used in building the branch trunk network here. So let's do it. Let's do it step by step. So here we also do we import everything from the super from like the same as all the neural network. We just import the same thing from this, which is the neural network module, and self dot init. Here self dot in1, we define it by in1, and self dot in2 we define it as in2 and self dot output neurons is going to be, well, output neurons, and we didn't assign this neurons. Yeah, now after that we need two networks. So these are the values we have to initialize, and we have to initialize another two networks. So branch network and self dot is going to be branch network, or actually just you can, and don't just we use it the same, or okay, and just, and self dot trunk network is going to be trunk network. Now we define these networks. So def branch network and it's going to take a self. And then what we need to do also here is the trunk network. So the branch network will take the whole values. So we said the whole values of u and put them into a network and get an output numbers or neurons. And the trunk network will take one value, which is the location we need to integrate this thing, and will give us another values or into the network, and then we have the whole system. So the branch network will start by equals neural network dot sequence or sequential, and I want it to be a little bit, neural network will be linear, and we'll take self dot in one and self dot net neurons. So it will start by, yeah, this way. I wanted to have this space. So start by having linear connections between the first input, and then we will have the neurons. So this the 40 points. Just make sure the spelling is right. Now after that, why is that? After that, what we will do is nn dot relu activation function, relu, and I don't know why it's like you have to write something before. And then we will have another linear, but we will take, this is going to be a hidden layer. And then what we will have is another relu. And after that, we will have a linear, but this time it will take from the number of neurons to the output size. So we put here, and this going to be the same, this, and we will take the output neurons. That's pretty much it. We can put this one. So input 1, and then it will input 1, and then it will expand, or not expand, it will contract, because this is the whole sequence. It will contract to 40 neurons, and then it will have a hidden layer of input 40 and output 40, and then it will have another or it will have the an output layer here that will connect from the input of 40 to an output of, we said here is 20. So this is the first network. The second network we need to construct is, we take this thing, the trunk network, and we will the same thing, sequential, and this time is also pretty much, we have the input become input 2, and it will have another hidden layer, and then we will add it again, and this time is here, we expand, this is another hidden layer, and this we can also add another hidden layer because it's a little bit not so heavy. Here we are or here we are telling the network what is the whole computation domain or the whole line we want to integrate, and here it's going to be the actual value. So we can add more hidden layer. Of course, it might even work without, even if you put, or most likely it will work even if you put one more layer here. The last thing is we need this guy. This is going to be the linear. I think it's, yep, this one. So input to neurons, input neurons to neurons, and neurons to neurons, and then this one to the output, and that's it. Let me close the thing. So here is the trunk network, this one, defined by this guy. This is the trunk network. Branch network is defined by branch network. And what else we need to do? We need to do one more thing, is another function, which is basically the main function of in PyTorch, the forward, or this is where we actually apply the network itself. We have to write it. So the forward network is going to be self will take x1 and x2, in which x1 will equal to self dot trunk, or not trunk, it will be the branch network, or this guy, branch. So this is the branch, and it will have an input value of x1, x2. Of course, x1 is going to be the input sequence, or the whole sequence, and x2 is going to be the other input. Here, self dot trunk, or I will take it as is better, trunk, and here is going to be the second input, that is the location, where like x, basically the exact location in which we need to do the integration. What else? X equals, this is a bit, this is, I need to explain a bit more, like this is okay. Now this is the main idea is already finished, like for regarding building the network. But what we can see here, just what we try to see now, it's basically, here is the branch, we already explained it, trunk, we already explained it. Now here we have a multiplication, and this is, we need to multiply the branch output neurons with the trunk output neurons. And in order to do that, we have something we call Einstein multiplication. And in Torch, we will write it this way. So Torch dot ein sum, and this is going to be the syntax. I will explain it in more detail as like now. I will just give, because this is a new concept actually, and we need to care a little bit. It's a multiplication between x1 and x2. So, but let me finish just writing this network, and then we will focus on Einstein multiplication. And here x, so basically some like a syntax that we will explain in details. And here is x equals just torch dot unsqueeze this one. We take x and unsqueeze it to 1, and then return x. So this is just unsqueezing. You it's just the shape has to be changed from a whole values of basically basically a whole values that looks like uh, as a string into simply one by one values. We will explain a little bit more in the later part in the evaluation about, because we will do also unsqueeze for that. Just we need to, rather than having one dimension like 100, let's say a data with a sequence of 100, it will make it like separated to each other. But let's focus about a little bit about Einstein multiplication, and we can just shift enter here. We have a trouble here. Ah, diff like this. Okay, this is already processed. So this will, I will ask in the, I will explain in the like basically in the evaluation phase, as we will do a lot of these things. And but here the Einstein multiplication, I would say, is more important. So let's do it here, and then just we comment it out. So let's consider x1 torch, basically torch tensor of this shape. One, oh sorry, this shape 1, 2, and we have 3, 4, and we have 5, 6, and another tensor. So it is, this shape is, we have 3 by 2, 3 rows and 2 columns. X2 here towards something, make it 2, 3, 4, 5. Just make it a bit different so we don't have trouble. We want just print x1 dot shape, and this is also x2 dot shape. No, I didn't. Ah, sorry. No commas. Okay, so we have two tensors this way, 3 by 2, 3 by 2. And now we will do the Einstein multiplications, or multiplication result equals torch dot in sum. Well, basically just apply the same syntax here. And just print this result. So these are the results. So he multiplied x1 with x2, and we got something that looks like this. What does it mean? Let's understand. Pi means the result, the values we are having is in the shape of p and I. And once, if you have a p and I, you take only p. So the result will be in the dimension of 3. That means if you have x1 and x2, and they have this two-dimensional well results or shape. It should have two-dimensional shape because you defined a p and I. This syntax has to be this way. It has to be two-dimensional. And then you multiply them, you will have a result that has the dimension of p. So b, 3. So it will have 3. So how can you calculate these numbers? We calculate these numbers by first multiplying 1 multiplied 2 plus 2 multiplied 3, and this will result to 8. So 1 multiplied 2 is 2, 2 multiplied 3 is 6, 6 plus 2 is 8. So here is 8. So I will write it. The first row, or the first element here, I don't element, equals 1 multiplied by 2 plus 2 multiplied by 2 multiplied by 3, 3, and equals 8. Second element will be 3 multiplied by 4. So 3 multiplied by 4 and 4 multiplied by 5. 4 multiplied by 5, and if you do the math, it will be 32. 3 multiplied by 4 is 12. 4 multiplied by 5 is 20. 20 plus 12 is 32. So we put 32 in here. Third one. Third element will be 5 multiplied by 6. 5 multiplied by 6, and which is 30, and 6 multiplied by 7, and is going to be 6 multiplied by 7 is 42, plus 30 is 72. 72, which is this guy. This is Einstein multiplication. Of course, what about if it's different? What about, just one last thing, just what about if we took the same thing and we multiply it, just very quickly, this guy here, pi will become I. We have two numbers. So what happened? He did now 1, he multiplied by 2, and 2 or 3 got multiplied by 4. So 1 multiplied by 2 is, just let me take my calculator. It's my calculator and just calculate. 1 multiplied by 2 is 2. 3 multiplied by 4, it's 9. Well, 3 multiplied by 4, 3 multiplied by 4 is 12, plus 2, this is 14, plus 5 multiplied by 6 is going to be 44. This guy. Actually, we can do it different. I just print. Just first element, and this is going to be 1 multiplied by 2 plus, so the dimension we put, the equation we put here is going to squeeze, that will change the shape of it, and the multiplication process has to change. I hope I'm explaining it, but like as easy as possible. I'm trying to apply the thing. So 3 multiplied by 4 plus 5 multiplied by 6. So this is going to be our guy. I hope it's, yeah, this element. Now, second element is, of course, pi, two-dimensional. We have 2 multiplied by 3. So 2 multiplied by 3, 4 multiplied by 5, 4 multiplied by 5, 6 multiplied by 7, 6 multiplied by 7, and you have the second element, 68. That's how it works. Last thing we do is our case. These are all two-dimensional array, but what we did is our dimensional array will look like this, like here 3, here 4, basically this way it will look. And x2, consider it, let's say 2, 3, 4, and then 5, because we have two lines that has to be multiplied each other. Now, what is the location? Now you say this is one dimension. It's not the one dimension because it has this two parentheses. So this is why it is not one dimensional. It's one row, 4 columns, and we apply exactly this guy, and we just call it results, the same as here. So we take this guy and we multiply it and see what is the result. So here, check. Result is, it's not p, is, yeah, of course, if we say p, it will be basically the one dimension. But if we put, okay, let's put it p. P is, when you put it one dimension, is 1 multiplied by 2, that is that's 2. 2 multiplied by 3, 2 plus 6, this is already 8. 8 plus 3 multiplied by 4, this is 12. You're talking about 8 plus 12, that's 20. 4 multiplied by 5, that's another 20, and you will get basically 40. So this is the number. If you do another thing, if you consider pi and you put it I, what will happen is he will put the last function to be, or the last result to be, we say pi, that means the last one is here, is I, and then we have to 1 multiplied by 2, it's 2. 2 multiplied by 3 is 6. 3 multiplied by 4 is 12. And 4 multiplied by 5 is 20. Okay, that's it. That's Einstein multiplication. This how it is, and I hope I explained it well. And basically, these are what we are going to use in here. So just make sure to we can keep them. But I'm afraid I'm using here x1 and x2. But anyway, it's not a problem because this is a class. It will be redefined while we now we do it. Like basically we set our model. But I would prefer, just to make sure, I will just take this guy in here and put it after everything here, because this will overwrite anything if we made any problem. And this guy, we just remove him, delete cell. Yeah, so just shift enter, And now we continue. So what we need to do is we need to define the model. The last thing we need to do is model equals deep on it, basically the name of the model, deep on it, and the number of neurons, we'll keep it the same, 40. Input 1 is m, input 2 is 1. Input 1 has to be 100 values. The whole, we say we'll put the whole sequence. Input 2 is 1, is no problem, and we can just print the whole model. And we have a problem. Self int doesn't have. Okay, we go to branch network 14. Sorry, it's a bit silly mistake, like just here it used to be a dot, and we have to put it the comma. It's just here, comma. Commas all over the place. We have to make sure. Comma. Okay. I found something that we have to. The reason now here, when I print it, I cannot see the model is because I forgot to put return the actual trunk, and here is return the branch network, or not the branch, we need to enter the branch. Yeah, now it's good. So with this, we finished building the model, and we can proceed for the training process.